Alright guys, I think I promised you in class that I would prove a little bit more of this proposition about limit theorems for functions, limits of functions. And so I did one case in class, and this is just another case to show you, just give you a little more practice I guess with how these theorems are proven. So if I have two functions f and g, and the limit of f of x is equal to L1, and the limit of g of x is equal to L2, then not surprising, the limit of f of x times g of x is going to be L1 times L2. So limits of functions respect multiplication is kind of the way that we could say that. So what we're going to need to do to prove this is we're going to need to show that the absolute value of f of x, g of x minus L1, L2 gets less than epsilon, right? So of course, we're kind of thinking in terms of our scratch. In terms of our scratch work, we have to kind of think about the absolute value of f of x, g of x minus L1, L2. And we want that to be less than epsilon. Okay, but the thing of it is that we can think of this is a little trick that we can do, is that we can add and subtract the same thing to the expression. So I'm going to subtract f of x L2, and then add f of x L2, and then minus L1 L2. Just squeeze that into the middle, and then use the triangle inequality. So what's going to happen here is I'm going to get absolute f of x, absolute g of x minus L2, and then on the second part I'm going to get absolute L2 times absolute f of x minus L1. Okay, now I want that whole thing to be less than epsilon eventually, right? This is going to need to be less than epsilon over here. So what I really am going to try to do is get each of these terms to be less than epsilon over 2. Okay? Now, I can make g of x minus L2 as small as I want, right? Because the limit of g of x is equal to L2. And I can make the absolute value of f of x minus L1 as small as I want, right? So what I'm going to do, I'm going to work on the second part first, okay? I'm going to choose a preliminary delta, I'll call it a delta 1, greater than 0, such that if 0 is less than absolute x minus c is less than delta 1, then I'm going to work on the f of x minus L1 part, okay? And what I'm going to do is I'm going to make that, I can force that to be less than anything I want. So if I want this whole second term to be less than epsilon over 2, then what I'm going to do is I'm going to put epsilon over 2 here, and then I'm going to divide by L2. Right? So if this part is less than epsilon over 2 times the absolute value of L2, and I then multiply that by the absolute value of L2, the result will be just epsilon over 2, right? Now there's one little problem with this, and the problem is that L2 could be 0. Alright, so just to prevent that from being a problem, what I'm going to do is I'm going to just add 1 to the L2 right there. Okay? That makes this denominator strictly positive. We've actually made this whole expression smaller, because the denominator is now bigger, right? So this whole fraction is now smaller, so this second term is actually going to be less than epsilon over 2 by the time we get done with it. Okay? So if we start with that delta, we're going to be able to control the second term and make the whole second term less than epsilon over 2. Now, I'd like to do the same thing with the first term. The first term, however, is a little trickier, because although I can make g of x minus L2 as small as I want, it's being multiplied by something that is not a constant. Okay, so the f of x is not a constant. However, this preliminary delta 1, actually, if we just assume that our final delta will be smaller than delta 1, then we actually can use this inequality to control how big f of x could be, right? Because if you just move the L1 to the other side of the equation, right, you basically can put absolute L1 there plus epsilon over 2 times the absolute value of L2 plus 1. See, this is just kind of technical. This is a technical proof, but not really that bad. So this f of x can be made less than this constant value right here. So I could imagine that is sort of playing the role of what the L2 did over here. So what I can do then is just choose another delta. So now actually we can kind of choose another delta. Choose delta less than or equal to delta 1. So I'm going to make sure that I don't make my delta any larger than it already was. Okay? But of course delta is still greater than 0, such that if 0 is less than x minus c is less than delta, that implies that, okay, so we're going to look at g of x minus L2 now. Okay? We want this whole first term to be less than epsilon over 2. Let me put that there. But I need to divide by, I want to divide by 1 over f of x, but I can't because that's not a constant, right? But I can divide by 1 over something larger than f of x that is a constant. So that's exactly what we're going to do here. L1 plus epsilon over 2. This is really messy. That's why I didn't want to do this in class. But that would basically be the expression right there. Okay? So it would look just exactly like that. Okay? Remember, we can make g of x minus L2 less than any number that we want. So we can certainly choose this. Okay? So now let me see if I can use that to write up the final proof here. Okay? I guess I'll just erase the statement. Don't really need that right now. Okay? So the proof, now that we've kind of figured out how it's going to work, let epsilon greater than 0 be given. Right? It's always how we start. Let epsilon greater than 0 be given. And then we have to choose a delta. Well, there's the delta over there. So I'm going to choose delta as described over here. Okay? So it has to be small enough that this is true and this is true. So we're choosing a delta such that this part is true right here and this part is true right here. So we've got those two expressions in our hands. And so then we just have to verify that that delta is going to work, right? So if I take the absolute value of f of x, g of x minus L1, L2, now I'm just going to bust it apart as I had shown you earlier. We'll have absolute f of x times absolute g of x minus L2. This was all done a little bit earlier. Absolute L2 times the absolute value of f of x minus L1. Right? So that's just using the triangle inequality. Okay? So then what we have here is that this is less than or equal to, okay, I can make f of x larger. I'm going to replace it with this thing. So right here I'm just replacing this with something larger. So absolute L1 plus epsilon over 2 times absolute L2 plus 1, all of that, okay? That's just this equation right here, this inequality right here. And then times the absolute value of g of x minus L2, which is less than epsilon over 2 times 1 over this whole thing right here, you see. So absolute L1 plus epsilon over 2 times absolute L2 plus 1, right? So obviously those are going to cancel and leave you with epsilon over 2 there, okay? In the second term, we're just going to replace, we're going to leave the L2 right here as it is, and then replace f of x minus L1 by this part, epsilon over 2 times absolute L2 plus 1. And clearly now, these cancel, right? You get epsilon over 2 here. They don't quite cancel, but the denominator of the L2 plus 1 is bigger than just L2. So you can replace this actually strictly less than epsilon over 2 again. And that adds up to epsilon. So this is then verifying the proof. So it's a little bit tricky, and especially this part over here, because you have to replace g of x minus L2 with something somewhat complicated. But anyway, I hope it makes sense. It's pretty technical, probably not something you need to worry about too much, but I just wanted to be thorough and complete and show you how something like that might be done. Okay? If you have any questions about it, feel free to let me know. Be happy to try to help you out. Okay, thanks.